Hello, ma'am.
Good evening, everyone. I'm Deval, and I'm a research scholar at IIT Madras. Today is our 11th year session on the topic design of steel structure. So, as we have started about the design of beams in last module, in this 11th week, you might have studied about the design of laterally and supported beams. So we divided our beams into two parts: laterally supported and laterally unsupported beams. And laterally supported beams, we have already done the designing and all the questions in the last week. And this week we will study about the laterally unsupported beams, and then how we can do the calculation of plastic section modulus. It depends on the type of section, like C section and I section, whatever type of section we have, how we can calculate the plastic section modulus, or what we will say it as symbolize at Z. Okay. Then you might have studied about the purlins. What are the purlins? Where are they used? And how we can design different type of purlins. And lastly, about the gantry girders, and what are the gantry girders, and what are the different components of gantry girders, and what are the design procedure for gantry girders. So if we go one by one, first is the laterally unsupported beam. So this is a basic definition of laterally unsupported beam given in IS 800. So uh, so if the resistance to lateral torsion work, how we are dividing laterally supported and unsupported beam is when when there is a bending moment, lateral bending, then we are telling that they are normally called as laterally supported beam. But if we are designing it for the torsional buckling, then we are calling it as a laterally unsupported beam. So in the case, if the bending is about the minor axis, or section is a hollow or solid bar, or in case major axis bending is less than 0.4, in these three cases, we won't call it as laterally unsupported beam. So normally they would be supported beams. So in case of laterally unsupported beams, how we are calculating the design bending strength? This is the formula we are using, where beta B is defined as 1 for plastic and compact section, and ZD by ZP for semi-compact section. Same way, ZP, ZD will be the section modulus, and normally we can find it from our steel table. Whatever section we are choosing, we will have their section modulus given for the particular thing. And then FBD is the bending compressive stress. So this bending compressive stress can be obtained from the table 13A or 13B. And this is the formula we are using for bending stress, xi LT Fy upon gamma m. Whereas xi LT is given by the reduction factor, and these are the different formula for our reduction factors. And all these formulas are already given in IS 800, so you can follow IS 800 for the same purpose. So next is if we have to find the slenderness ratio. So for slenderness ratio, this is the formula, under root beta B ZP Fy divided by MCR. So MCR will be our elastic critical moment, as we have calculated it 8.2.1, which will come in the next clause. Okay. So what are the different design steps of laterally unsupported beam? So first step is we will be given some load. We will factor the load and we will calculate the service load, and factor loads are calculated. Then second step is we are calculating the bending moment and shear force based on our factor load. So it will depend on our loading condition. We have seen in our previous lecture how different loading condition will have different K value. So same way, we'll calculate our bending moment and shear force. And after calculating this thing, we will find the trial plastic section. Like we will find the ZP value, plastic modulus value. Uh, from this ZP value, we will check in our steel table and calculate the we will select a suitable section for our design. So normally we are taking ISMB, ISLB and ISWB. So normally these three type of section are preferred for our beam selection. We talked about it that normally we are taking I section as a beam section. So now we will select a section based on our ZP value, and after when we have calculated, we have selected our section, then we will classify a section as plastic, compact or semi-compact based on their P upon TF and D upon TW value. Okay. So this is the table given in IS 800, where we are telling B upon T value. Based on our B upon T value, how this different classes can be divided, plastic section or compact or semi-compact section. Okay. Next is the after our section is fixed, after we have divided our section as a plastic, compact or semi-compact, we will calculate the design shear strength. And our design shear strength, after calculating the design shear strength, we will check it for the shear capacity, that V should be less than VD. If V is less than VD, then our design is good. Then if V is less than VD, then our section is safe against shear. If it is not, then we will we will change the section. We will choose a higher section and then we will repeat the complete procedure. After that, after checking for design shear strength, we will check it for the design bending strength. So design bending strength, MD is given by beta P ZP into FBD. Same way, if our MD is greater than M, then our section is okay. If it is less, then we have to again change the section and repeat the steps. Okay. After checking it for shear bending, we will check it for the deflection. So in table 6, different deflection formulas are given, deflection checks are given. So using that table, we will check our beam for the deflection. And the next thing, we are checking it for the web buckling. So web buckling formula is given by FWB is equal to AB into FCD. AB will be the area of our web area. Like this is our I section. I hope you guys might know by now that this is our flange and this is our web. So our web area at the neutral axis will be our AB, and which is normally given by B into TW, and FCD will be the design compressive strength. So again, our web buckling strength FWB should be greater than the VD. If it is greater, then design is okay. Otherwise, again, we have to repeat our section. Last thing we are checking is for the web crippling. So web crippling formula is given by B2 into TW into Fy divided by gamma m naught. B2 is all these formulas we have seen in the last lecture. So same thing we are following here. And same way, our web crippling strength should be greater than our design shear force. If it is greater, then our design is okay. Okay, so this is the basic design steps we are following for the laterally unsupported beams. Next thing, what you might have studied in this week would be the purlins. So purlins are like a lateral uh, reinforcement kind of thing we are provided, which are supporting the sheeting. Like if sheets are provided, so to support those sheet, we are providing some horizontal beams, which are called as purlins. So these are the horizontal beam used for the structure support in building, mostly in roofs. So they are provided between the, if this is a roof truss, this is a roof truss, so these are our purlins which we are provided. So they are the members which are resting between roof truss and sheeting. So above this we will provide some sheeting, so these are called as purlins. So how we are designing purlins? So we have different formulas for design of our purlin is, firstly, we will calculate the bending moment. So in case of purlins, we are calculating the bending moment in two directions. One is about UU axis, one is about VV axis, yani कि horizontal and vertical axis. So these are the formula for the same, where P dash is the gravity load acting in the VV axis, and it will include self weight, live load, and snow load. So this is the formula, and HH is the horizontal load acting in UU axis, and it will include only the wind load. So it is given by P sine theta. Now L is the total span of purlin. So in this case, total like if this is our truss area and back truss is like this, our purlins are provided in this direction. So center to center distance between these two trusses will give us the span of our purlin. So solving these two equations, we are getting mu will be given by h plus p cos theta L divided by 10, and mv is given by p sin theta L divided by 10. Okay. So next thing is that we are providing some checks for our purlins after calculating the moment. First check is the for the biaxial movement of channel and I section. Our interaction formula is given by mu upon mdu plus mv upon mdv. And mu and mv we have calculated before, and du dv are the design bending moment about both axes. So purlins are subjected to biaxial bending, I'll try. Then after calculating bending moment, we will calculate same way. We will calculate our section modulus, and based on the section modulus, we will decide our uh, section. Like we will select a section for our design. So this is the different design procedure for in case we are having channel section or eye section, how to design a channel or eye section purlins. First thing is we have the span. We calculate the span. So normally we will be given total length. So center to center distance between two trusses will give us the span of one purlin. Then we will calculate the two type of load: gravity load P and wind load H. And from this loads, we can calculate our P dash and H dash, the formulas we have seen before. And from there, we are calculating our bending moment and shear force using the factor loads we have calculated. And from the same procedure, from the bending moment, we are calculating our section modulus. And from the section modulus, we are checking the section classification as per table 2 of IS 800. Okay. Next is same way we check our design for the shear capacity. Then in both axes, in y direction as well as z direction, and then we will check it for the local capacity using our interaction formula. Last is check for the deflection. And so this is like same procedure we are following for all type of designs. And now if we go for the angle section, in case we are not providing eye section or channel section, then we are, in case we are providing angle section for our purlin. So in that case, steps will be same, just the formulas are changing. So here our bending moment is given by WL square by 10. Small w will be UDL in case we have UDL, so WL square by 10. If we see that I section or channel section, our mu is calculated as this formula, PL by 10 or HL by 10, where it is H plus P cos theta L by 10. In case of an angle section, our mu is given by WL square by 10. And same way, then we will calculate our section modulus. And this formula is also different than the formula we are using for our channel section. So this is the formula we are using for our channel or eye section. And this is the formula we are using for our angle section. So in the case of angle section, we are assuming if our depth is 145 of span and width is 160 of the span, a trial section of angle corners is arrived. Like we are calculating our trial section. And if it should be always like our depth and width should always be less than the specified value to ensure that deflection criteria is followed. If we are increasing our like we should prefer that whatever depth and width we are choosing should be less than the specified value, like should be less than this depth value and this width value. So in case we are span is 8 meter, so 160 of 8 and 145 of 8 will be our D dash, and let it be B dash. So whatever D and B we are selecting should always be less than the D dash and B dash value. Okay. So after this, we are finding our suitable section, and then we will calculate the leg length of the angle section. And modulus of section should be always greater than modulus of section calculated. So this is the required modulus of section. It should be greater than the modulus calculated. Okay, so this is what was there in Purlins. Uh, 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 Example design you might have already studied in class. We will just solve some questions which is related to your assignments afterwards. Last thing you might have studied in this week would be the Gantry girders. So you might have seen in some industries and all, Gantry girders are provided at the uh, we provide gantry girders in our industrial area normally to carry our load from one place to another. So this type of structure you might have seen. So sometimes these are the different components of our gantry girder. So we have our crane bridge, which moves in this direction. So this crane bridge is moving over our gantry girder. So here we are providing two eye section. So this eye section will go in this direction fully if we see in a 3D way. So this is our gantry girder over which our crane bridge will be moving. And over the crane bridge, one trolley or crab will be moving to take the things from left to right direction. So this crane bridge will move in forward and backward direction, and this trolley will move in left and right direction. And above our gantry girder, we have one rail and then one wheel. Above this wheel, this crane bridge is there. And then we have this hook which is connected to our trolley or crab, and there is a minimum approach, like minimum distance to which this hook should come near to the gantry girder. And this is the beam and column joint, and this is the top view of the same thing. So this is our crane bridge, this is our trolley, and this dark areas, if you see, these are our wheels below which, and this two things, these are our gantry girders. Okay. So these are the different components of our gantry girders. So we have a crane over which we have crab or trolley, hoist, power transmitting devices, cab, which houses the control and over. Then we have rails, as we have seen above our I section. So this is our gantry girder I section. Over this, we will have rails over which this crane will move, and then this gantry girders, and then we have the columns with brackets which are supporting our gantry girders. Okay. So these are the different components of our complete what we'll say complete runway system. So what are the different type of loads which are acting in our gantry girder system? So first thing is imposed load. So we have some vertical loads from the crane, then we have some impact load from the crane. Next is the longitudinal horizontal force acting along the crane, and last is the lateral thrust across the rail. So in calculating the above force, crane should be positioned such that it gives the maximum design forces in the girders. So how we are keeping our crane, or how we are keeping our trolley, we will design accordingly in such a way that we design it for the maximum forces in the girder. So apart from these four type of imposed load, we have additional impact load. So if we have electric type of cranes or a hand operated cranes, based on different type of cranes, our additional load will be, we are taking 25% on static wheel load. If we have hand operated, we are taking 10% of static wheel load. This is for vertical loads. Then is the horizontal forces transfers to the rail. Okay, in the direction perpendicular to the rails, if we are having horizontal forces, for electric overhead trains, we are taking 10% of the weight of crab and weight lifted on the crane. In case of hand operated, we are taking it as the 5% of weight of crab and weight lifted on the crane. And in case we have horizontal forces along the rails, then we are taking it as the 5% of the static wheel load. So these are the additional impact loads we have. Next are the lateral loads. So what are the different lateral loads which are being used in the gantry girders? As the crane moves with the load, lateral load is developed due to the application of brakes or sudden acceleration of the turbine. So according to IS 875, 10% of the W for EOT cranes, EOT means engine operated, sorry, for electric overhead cranes. So for these type of cranes, we are taking 10% of the W, and where W is the total weight, which include the lifted weight and the trolley weight. Next is the longitudinal load. So as the crane moves longitudinally, loads parallel to the rails are caused due to the braking or acceleration swing. So this load is calculated, is called the longitudinal load and is transferred to the rail level. So normally longitudinal load per wheel is taken as 5% of the wheel load. So this is the formula, WG is equal to 5W upon 100. So next thing in gantry girder is, these are the different type of loads we are seeing. Next thing is deflection. So in table 6, we have permissible deflection for all type of structures we are using, whether it's beam or gantry girder or anything. So these five are for the gantry girders. When we are using manually operated cranes, then we are taking maximum deflection as L by 500. When we have electric overhead cranes up to 50 ton, then it will be L upon 750. When it is more than 50 ton, then it will be L upon 1000. Then we have other moving loads such as charging car or etc. If we have this type of load, then we are taking it as L upon 600. And in case of lateral deflection, we are taking it as 10 mm or L upon 400. Okay. So, as we were discussing about imposed load that we are calculating our load in such a case that we have the maximum, we calculate the maximum force. So, in that case, how the load should be placed to get the maximum load. First thing is the position of crane hook for maximum vertical load on gantry girders. So, our crab or our trolley should be placed as close to gantry girder as possible. So if we see this RA and RB, so these are the two different rails we have, and gantry girder will be just below this, and this we will see it is our crane moving, and this will be our trolley. So to get the maximum force, our trolley should be placed as close to our gantry girder as possible. So if let us imagine it is placed as a distance L1, so we will calculate reaction at RA and RB. This will give us the reaction in our gantry girders. So this is the first thing. Second thing is, for the maximum effect on gantry girders, our crane wheels should be placed at what should be the position of our crane wheels for the maximum effect on the gantry girders. So if we see, sorry, our crane wheels, if this is one gantry girder, okay, let's see if I can draw it. So our crane will be like this. These are our two gantry girders. This is our crane and this is our trolley. So first step is we are designing the position of our trolley. So a trolley should be as close to gantry girder as possible. Second thing is we are designing the crane wheels. So these four will be our crane wheels. 1, 2, 3, 4. So if we imagine one gantry girder, this is our one gantry girder. On this, where should be our crane wheels so that we are getting the maximum effect on our gantry girder. So this is the position of our crane wheels. Then we will calculate the reaction on C and D. We'll calculate the bending moment, shear force, everything. Last thing is the where should be the position of wheels for maximum shear on gantry girder. So to get the maximum shear on gantry girders, our first wheel should be at one edge of our gantry girder, and second should be at a, like, if crane wheel distance should be given, let it be it is given as A. So this is a crane wheel distance. So to get the maximum shear on the gantry girders, our one of the wheels should be placed at the one corner of our gantry girder. Okay. So these, when we go for the design of gantry girder, first thing we are fixing our position of trolley and crane in such a way that we are getting the maximum effect on our gantry girder. So these are the three type of position we are choosing. First thing is the trolley thing, where should be the trolley. Second is where should be the wheels of our cranes for maximum effect. Third is the where should be the wheels of the crane for the maximum shear. Okay, is that clear to everyone? Okay, next thing is the fatigue effects. So, in case of our gantry girder, since we have moving loads on our gantry girder, there can be a chances of fatigue. Fatigue means a failure due to multiple loads, continuous loading. So, for fatigue effect for light and medium duty crane, is given by this formula. And if we know actual number of stress cycles, how many stress cycles are there, then we should know that our stress cycle should be less than 5 into 10 is power 6 of 27 by gamma MFT divided by gamma F raised power cube. And in case of our heavy duty crane, our gantry girder must be checked for the fatigue. So these are the different partial safety factor and the stress ranges which we have for this formula, gamma MFT and gamma MF. So you can see these things. Next is the what is the design procedure for the gantry girders. So design some design example was there. I think that will come in last week. Oh, sorry, next week. So for now, only design steps were there in this week. So first thing is we are calculating the maximum wheel load. So maximum wheel load means we are calculating the maximum vertical load that can act on our gantry girder. So what we have seen is our where should our trolley be kept to get the maximum load. It should be as near to our gantry girder as possible. So first thing we are calculating that maximum vertical load, maximum wheel load. Next is the with suitable positioning of frame, we are determining the maximum moment and shear force on gantry girder. And then we will add our impact load onto it, like we have seen 25% additional for in case of electric train and 10% extra in case of our hand operated train. So that additional contribution due to impact load will be added. Then after this, we are calculating our maximum shear force. So to calculate maximum shear force, what we are doing, we are keeping our train one wheel over the corner of our gantry girder. So one wheel will be here. Using this, what we'll say, using this symmetry, we are calculating the maximum shear forces on our gantry girder. After this, we are calculating the lateral forces on our girder, and then we are calculating bending moment and shear force from these two steps. From bending moment here and shear force here. From this shear force, we are calculating the lateral force. And after calculating our bending moment shear force, again we will calculate our ZP value, section modulus. From section modulus, we will select our any I section, mostly I section we are choosing. We are select an I section with channel section. And using these section, again we will provide some different check to it. So we are doing a trial section. After selecting a trial section, uh, these are the different condition that should be preferred. We that our economic depth of gantry girder should be 1/12 of the span, and width of flange chosen should be between 140 to 130 of the span. So these factors we should make sure that are followed when we are choosing a trial section. After getting a trial section, we will get the properties of our section. These all properties are already given in our steel table. So based on B upon TF and D upon DW ratio values, we will classify a section as plastic compact or semi compact section. After this, we will check our section, like we will calculate MDS, and if it is less than 1.2 ZD or Fy upon gamma m naught, then our section is okay. Otherwise, we have to repeat the trial section. However, for laterally unsupported compression flange, the buckling resistance is to be checked with the design bending compressive stress FBD. So about y-axis, same formula is there. That was x-axis, this is y-axis. And then we are checking, we are checking our section for the local capacity using interaction formula. So if this is followed, then our section is correct. Again, same thing we are checking. I will check our section if it is safe against shear, safe against buckling and bearing stiffness, safe against deflection, and lastly for the fatigue. Okay. So this is what you might have studied in this week completely. If you have any problem, you can ask me now. Otherwise, we'll go to different questions which will help you solve the assignment for this week.
Ma'am, in the spreadsheet,
Yeah.
only 4 weeks videos only uploaded. Where are the other weeks, ma'am?
I will upload it by today. Forgot to upload. I will upload it. I think
Okay, ma'am.
PPTs I have already uploaded all. I will check that also. Will upload. You can check the PPTs. PPTs are, I think, already uploaded. Videos I will upload by today.
Okay, ma'am.
Okay. So the first question is calculate the trial plastic section for the given factor bending moment data. So M is given by 45 kilonewton meter. To account for the later torsion buckling, assume ZP value to be 40% higher than the calculated value. So first we have to calculate ZP and then we have to increase by 40%, and then we have to select a section for it. Anybody who want to try it out? Okay, so for how we are calculating is ZP is M into gamma M naught divided by Fy. So nothing is given, so then we are taking Fy is 250. Normally we are taking that only. And gamma M naught for our laterally unsupported beam, it is given by 1.1. So using this, we are calculating ZP as 198 into 10 is to 3 mm cube. Next thing is given, we have to increase this by 40%. So increasing it by 40%, we are getting our ZP value as 277.2. So if we see here, we will select a section which is greater than the which have ZP greater than the calculated ZP. So in this case, we have it as D. Okay. So we are taking ZPS 338, which is higher than 277, and the section chosen is ISLB 250 at 27.9 kg per meter square. So next is what is the additional vertical impact load for electric overhead cranes? So we have seen the table. From the table, if we see in case of vertical loads and electric overhead cranes, additional vertical load is given by vertical load. Electric overhead cranes, it is given by 25% of maximum static crane load. Right? So the next question is, for biaxial movement of channel and I section, the interaction formula is given by mu upon mdu plus mv upon mdv should be greater than equal to 1, or mu upon mdu square plus mv upon mdv square should be less than equal to 1, or mu upon mdu square plus mv upon mdv square should be greater than equal to 1, or mu upon mdu plus mv upon mdv should be less than equal to 1. We are using since the first slide, so correct answer is mu upon mdu plus mu upon mdv should be less than equal to 1. Okay. Next question is, gantry girders can be designed as laterally supported beam using channel section only as laterally unsupported beams. First thing is first statement only we are telling our gantry girders are laterally unsupported beam. So this is the incorrect answer. Second is if you remember, we are seeing our gantry girders design. We are telling we are using our I section along with channel section. So we cannot design only with channel section. So correct answer will be only 3. Okay. So next question is, as per IS 800, the maximum deflection allowed for the purlin is span upon 200, span upon 180, span upon 300, or span upon 120. So if you remember this table, table 6 of deflection limit. So in case of purlins, we have elastic cladding, brittle cladding, two type of cladding, and it is given by span upon 150 and span upon 180. So here nothing is given, but like which type of cladding is there. So we will choose whichever is the option given here. So span upon 180 will be the correct answer. Okay. Next question is, what is the maximum permissible vertical deflection of the gantry girder having span of 8 meter when the cranes are manually operated. So again from the deflection limit table, if we see in case of our gantry girders, so these are our three gantry girder cases. Now what is given to us? Cranes are manually operated. So manually operated gantry cranes, it is given as span upon 500, right? So span is given as 8 meter. So divided 8, we will convert it into mm. 8,000 divided by 500 gives us a 16 mm of deflection, right? Next is the what type of load causes fatigue effect in gantry girder? Lateral load, impact load, moving load, longitudinal load. So this is very simple answer. Due to continuous moving load, we are having fatigue effect in any type of structure, whether it's beam or any. So next question is a design question. So we are given an industrial building is to support a galvanized iron sheet roof for the following data. Slope of truss is given by 28 degrees. Spacing of truss center to center 5.5 meter. Spacing of purlin center to center 2.5 meter. Wind speed as 48 meter per second. Weight of galvanized sheet as 105 Newton per meter square. And dead load of purlin is 130 Newton per meter. So what is asked is calculate the magnitude of the factor bending moment in the direction normal to roof and along the roof respectively. You can try for 2 minutes, then solve. We will see the solution then. So first thing, what is given to us? So steel of grade as 410. So for our Fe 410, we are using FIS 250 MPa. Then we have given weight of galvanized corrugated sheet. So our weight is given by 105 Newton per meter square, and we will multiply it by the spacing of purlins to get the weight in Newton per meter. So this is the weight of our corrugated sheet. Then we have the dead load. Dead load of purlin is given by 130 Newton per meter. So total dead load of our purlins will be dead load of sheet plus dead load of a single purlin. It is 392.5 Newton per meter. Okay. Next thing is all this dead load, they are acting down vertically downwards. So this is our dead load, and this is our purlin. It is given at 28 degrees Celsius. Oh, sorry, not Celsius, 28 degree angle. And then we are calculating the component of our dead load in the direction and in the perpendicular direction. So component of dead load normal to the roof is given by cos theta. It is multiplied by cos theta. It will give 346.56. And the component of dead load along the roof, it is given by into sin theta. So if you convert it like this is what is given to us. This is 28 degree, then this will be 28. This is our weight, and this will be our W cos theta. This will be our W sin theta. So using this formula, we are getting the component of our dead load in the direction and normal to the direction of the load. Now what is asked to us? We have to calculate the magnitude of bending moment in the direction and perpendicular to the direction. So what else is given to us? Wind pressure is given to us. So sorry, wind speed is given to us. From wind speed, we are calculating the wind pressure, which is given by 0.6 Vz square. Vz is 48. So using this formula, we are getting wind pressure as 1382.4 Newton per meter square. And normally our wind force is acting normal to the roof. Wind force will be always normal to the roof. So calculating the wind load, it will be pressure into this spacing of this 2.5 this spacing into 1. Thus we are calculating our wind load in Newton per meter, which is acting normal to the roof, right? So now we have two type of load normal to the roof. Sorry, one is due to wind and one is this component of dead load normal to the roof. So adding these two loads, we are getting total load on the purlin normal to the roof. Adding these two loads, then we will factor these two roof loads. Factoring means multiplied by gamma into center to center spacing, right? Center to center spacing is given as 5.5 meter. So using this, we are getting factor load in the direction and normal to the direction. And using our formula for the movement, TL by 10, HL by 10, using this formula, we can get the bending moment normal to the roof and along the roof. Okay. You can use, instead of multiply 5.5 here, you can actually use like small p into L square by 10 also. Just factor it here and then you can multiply it by 5.5 for whole square divided by 10. Same way you can use it here also. Okay, is this question clear to everyone? We'll go to the next question. Determine the plastic section modulus of ISMB 450 at 72.4 kg per meter about the strong and weak axis respectively, neglecting the fillet weld. So the relevant properties of ISMB is given by D. D is given to us, DF is given to us, TF is given to us, DW is given to us. So using two ratios, we can calculate. So this is the formula which is given to us to calculate the PZ value, ZP in the Z direction. BF TF into D minus TF plus DW, D minus 2DF divided by 4. Using this, we are calculating section modulus in Z direction. And using this formula, we can calculate our section modulus in Y direction. Okay. These are the direct formulas which are already given in your IS code. You can use these formulas. So this is the last question for today. Calculate design normal fatigue range FF and shear fatigue range TF respectively for a gantry girder from the given data. Number of stress cycle NSC is given as 3 into 10 to 5 cycle. FF and TFN is given as 59 Newton per mm square. So these fatigue formulas which we have already seen, we will use the same formula. So FF is given by FFN into cube root of 5 into 10 to 6 divided by NSC. So we had the formula of NSC. We have just converted that formula. I will show you that formula. So this was the formula where our NSC should be less than 5 into 10 to 6, 27 divided by gamma MFT divided by gamma MF whole cube. So now we are calculating fatigue stress F. We are calculating the F value. So F will go there, NSC will go here, it will come as cube root. Sorry. So using the formula, we can get our FF value, which is coming as 150.71 Newton per mm square, and tau F value will be similar only in for fatigue range, normal fatigue range, it will be FF into is equal to FFN. In case of shear range, it will be tau F is equal to tau FN. other thing will be same. It is cube root. It is root 5. Okay. So these are the answer. So that's all for week 11. In case you have any doubt, you can ask me now. So if there are no doubts, then we'll close the class today, and I will upload all the videos and presentation by today itself. Okay. Thank you.